Hello everyone, welcome to this new video where we are going to go through 1475 pseudo palindromic path in a binary tree. So basically what we have an input is a tree and we are supposed to find out how many paths of the tree are actually pseudo palindromic. And it has been defined here that a pseudo palindromic path is actually a path where we have at least one rearrangement that will give you a palindrome. Let's say we take this tree for instance. This path moving from 2 to the end here is actually a path consisting of 2, 3 and 3, and a palindrome can be 3, 2, 3. 3, 2, 3 is a palindrome. Make sense? And here the same, you have 1, 1 and 2. So a 1, 2, 1 is a palindrome because it can be read the same from the left and from the right. So that being said, how are you going to approach this problem? What will be our approach of solving this? Now we know that we are supposed to find the path that we have an rearrangement that will give us a palindrome. So one thing that I can do is, first of all, understand how to find out what is a path, right? A path is actually a way down from the root till a leaf. So here we have 1, 2, 3 leaf. So we are going to have 3 paths. The first path is actually this one, which is moving from here. The second path is actually this one, and the third one is actually this one. That are my paths. And for each of the paths, if it can be rearranged and form a palindrome, then it is actually a pseudo palindromic, and then for that we are going to count it as one solution. So now that we are aware of how to find out what is a path, the second thing is how to find out if a path is actually palindromic. So for that I'm going to share with you an observation. If we have something like 2, 2, 1, 2, 2, it's a palindromic because it can be read the same this side and this side, right? If you have something like 2, 1, 2, 1, 2, this is also a palindromic. So for you to find out if a rearrangement is a palindrome, you just need to make sure that we have at most one odd occurrence. What does that mean? If we have an element, let's say 3, that appear 2 times, so the element can be placed one at the left, one at the right, and that is actually a palindrome, because when you're going to read from left to right, you're going to have the same value reading from right to left. But if you have let's say a scenario where you have an element appearing with one occurrence more than one, let's say I have 1 appearing 1 time and then I have 2 appearing also 1 time, even if I have 3 here, 3 here, 4 here, 4 here, this will not give me a palindrome with no arrangement because I have these 2 elements that are going to break it. But if I have a 1 here, this one can be tied to this one, and then this one will make me a palindrome because I will have at the end only one element with an occurrence of 1. And if I have again a 2 here, in this case I will have 0 element with an occurrence of 1, and this will still give me a palindrome. So basically my idea of finding the palindromic element will be to check if the count of my element, if the count of odd element is actually less or equal to 1. Because if it's actually equal to 1, it's dead, we can't have it. If it's actually equal to 1, we can have it. If it's equal to 0, we can have a palindrome, but otherwise we can't. Now that we are aware of the logic, how do we implement that? That's the most important thing. Now for the implementation of this, my initial thought was to use a map, and then I'm going to show you my approach of using a map, and I'm going to update it to make it more better and using bitset operation. So the idea of the map is that, okay, I'm here, I have an element of occurrence 2, so my map will look like this. I will have 2 appearing 1 time. And then while moving, one will be here, these statues will be used for this and this. So at this stage I will have two map. In fact, since I'm using recursion, I don't need to really count that. So I'll just take the initial map and I will say, okay, we are now here. If we are here, we are just going to return a map now with the with the two appearing one time, plus three appearing one time also. And this one will actually return this one and this one. So I'm first taking this one. This one will give me a map of theory appearing two times instead, because we have another theory here. And then after this, there is nothing at the left, nothing at the right. This will be the statue of my map. And what I will do is that I will check how many elements do I have here with an occurrence of 1. And yes, 1. And based on what I just explained previously, if the occurrence is actually 1, you just need to return you just need to count it as a valid path. So you count it. So given that approach, what would the code look like? The code will look like this. Basically, you have your map here, which I will call it count. And then I'll say, okay, for each of the element, I count the element, like I count the occurrence of the element in my count. And then I don't even need this. This was for an optimization which didn't work, so I don't need this, or I can put it directly inside here because it's to count the number of occurrence. Okay, so now that I've added the value of this element, I'm checking if the left is equal to null and the right is equal to null. That means it is a lift, and if it is a lift, it's actually a path. What I need to check if it is a valid path. A valid path now has been defined with a path that the number of occurrence is actually less or equal to 1. So I'm first going to count the number of odd occurrence, and then for each of the number of odd occurrence, I'm going to add it here, and at the end I have the count. I just need to check here if the count is actually less or equal to 1. I will return 1. I will return 0. If the answer is actually less or equal to 1, that means we are in a scenario where it's a valid palindromic path, so I return 1, so I count it as a solution. Otherwise I return 0. And then after this, I just need to check if we have a left, we are going to also consider going through the left. If we have a right, we are going to consider going through the right, which is actually a pretty good solution in the approach. It's actually working, but the only issue with this is that it is extremely slow. Let me first show you something. Initially I was having a map here, but another map which is actually working pretty well. Let me run, you will see. So it is working pretty well. You see everything is green, but it is, you have a time limit if you run this with a map. So this is what I was having initially. And then you see you have a time limit here, and after a couple of tries, I changed my map to another map, which kind of easier my memory usage. And then honestly, I wasn't expecting just the change to help me pass all the test cases, but it did. It passed all the test cases, but with a really bad time. You see, so I was having a runtime of 1853 bit 5% of C++ user. This is actually a valid solution, but I was thinking of something better, and I came up with another solution. Because what is actually my bottleneck here is the fact that I'm going with my map all over and all over. So I'm reusing a big map, moving from recursion to recursion. So what I decided to use is an int here. Now, before telling you what I've decided to use, let me share with you my approach. So my idea will be as follows. I know that if I find an element, maybe 2, what I want to do is that I want a structure where the next 2 that will come is going to erase the previous. Because if an element is actually removing or erasing any previous element that he is seeing, then we are 100% sure that at the end of the day, we are just going to have our structure with the element that appear only one time or odd number of time. Let's say you are a scenario where you have two appearing one time and three appearing two times. So at the end of the day, this one you just want to know that two is appearing one time. You don't want to know that three appear two times. But if you were having three appearing three times, in that sense you wanted to keep in mind that you have three that is appearing one time. That means it's actually an element that hasn't been paired. So that is my idea. And for me to have that, I'm going to transform the number of occurrences in bit representation. So I will say the 2 will be represented with 1 and 0, 0. The 3 will be represented as 1 and 0, 0, 0. 1 and 3, 0. I'm 100% sure that if I'm keeping a scenario where I will have this represented by this represented by this, if I'm summing them, this will not actually affect this one, in the sense of I will still know that I have 1 3, I have 1 2 and stuff like that. And adding to that, I'm going to use the OR operation. You know why? Because A or A will actually give you 0. So if I have a sum that is keeping the bit representation of each of the occurrence, each of the element that I'm seeing throughout my looping, in a way that they are not affecting each other, like I said here, and adding to that, I'm using an OR operation. I'm 100% sure that at the end of the day, I'm going to have like just a representation of element that hasn't been paired. And how am I going to use that? If I have maybe this, let's say I have this at the end. If I have this at the end, that means I have two elements that hasn't been paired. The element with 1 0 0 0 and the element with 1 0 0. So at the end, I just need to count the number of 1 of my solution. And if the number of 1 is actually equal to 1 or 0, that means it can be a valid palindromic array. And you'll see that only this representation will actually be it will be wow. Let's see how we can implement that. So here we are just going to have an int count. I prefer to call it count to keep things simple, even though bit count will be better. And then I'll say here the count will be equal to the count, or this is actually what I was saying. This shift is actually you are actually shifting from one a certain number of elements, which is actually corresponding to the val. So if the val is actually 2, it will shift 2 times and it will add 2 0. So it will give exactly what I was showing previously. And then this will actually be changed a little bit, in the sense of you don't need to loop anymore. You just need to have like a bit set here of 10. Why am I going with a bit set of 10? Because we set here that the note are actually, the value of the note are actually from 1 to 9. So the maximum value we can have from the note is actually 9, and 2 power of 9 can fit into 10 digits, I would say so. So that's why I'm taking 9. I'm taking 10. So after this, I'm just going to say we are taking a bit representation of the count. Once you have it, you just need here to check if so you just need to rename the variable. So I will say bitset is actually taking a as initial value the count, right? Now that we have it here, the next thing we need to do is to count the number of 1 in this count. That's why I was saying count is not a good name. It's better to use bit count. Yeah, it's better. Count is not a good name, it's kind of confusing. And then here you can just use a bit count, a bit set of the bit count. Okay, now makes sense. So now just make the count function is a count on bit set that count the number of 1 in a representation, and here you just need to return. You don't need to change this into 0. Let us run and see what it gives. We have an error somewhere. What is our error? So where it is saying that our bit count, this operation is not okay. Val, okay, I have a double L here. This actually, he's not also happy with this. Why he's not happy with this? Because count doesn't exist anymore. Yes, you see, first of all, you see 0 millisecond here. Let us submit. Now we are beating 97.86% of C++ user, and in memory we are beating 99.20. So this, because of this change, we are able to really improve our overall performance of our algorithm. So this was my approach of solving this. I hope you do enjoy it. Feel free to give me any input. I'll be really happy to interact with you regarding this. See you on the next video. Ciao.